Unit Operation Classroom. Today we are discussing flow rate and turn-down ratio in a hyperbolic control valve. My name is Shekhar Bhattacharya. A control valve with hyperbolic characteristics. We'll look into what is hyperbolic characteristics. Has a turn-down ratio, which is defined as the ratio of maximum flow to minimum controllable flow. We'll see more of that. What is meant by it? Of 50. This value is given. The flow rate through the valve at 70% opening, one set of data point is given that at 70% open position has the flow rate of this much of the liquid. Assuming constant fluid density and pressure drop, we are assuming this to be liquid, but this could be gas also across the valve. Which one of the following is the flow rate through the 30% opening? So 70% value is given, we have to find out 30% opening. So basically, we have to find out what's the hyperbolic characteristics. Okay. So let's look at the control valve. So this is a typical control valve here. You can find out the details in any textbook here. So this is the protein and fluid valve, and of course the stem position keeps on moving to allow more or less of the liquid or the gas flow. The hyperbolic characteristic is given by this equation right here, where R is a turn down ratio. We'll see what turn down ratio means. Flow rate at any X position. So what is X is the valve opening fraction. So basically, what is X? X, so the stem position moves. So the X is actually the actual stem displacement from the reference of the closed or the minimum position divided by the total displacement from the closed or minimum position to full open. From minimum position to full open. So that's just the ratio. So this ratio goes from 0 to 1. Of course, 0 means it's almost, valve is almost closed, but it's not fully closed. It's really called minimum controllable flow. And when X is equal to 1, it's called the maximum controllable flow. So what it really means is that it's not fully closed. That means not totally shut off, or it is not fully open. That means 100% open. If it is 100% open, then of course there is no the control the characteristic. The flow is not controllable. So it's slightly little different from the fully closed or the fully open position. So that's why it's called maximum controllable flow and minimum controllable flow. So this is slightly different from total shut off and totally open. Okay. So R is the turn down ratio. It's called rangeability. How is it defined? R is given as the Q max over Q mean, maximum flow rate. That means when we have the maximum controllable flow and this is the minimum controllable flow. This ratio is 50. So it's the ratio of maximum controllable to minimum controllable flow. Highest or the lowest flow where the valve responds properly. That means following the valve characteristics to changes in valve position. That's what's meant by controllable flow. Okay. So Q mean over Q max, of course, R is given. So at X is equal to 0, of course, this is equal to 0. So at Q mean, so this is going to be equal to 150, right? So basically, that's what it is. So Q max is of 50 times of that of Q min. Let's look at the curve. How does it look? So this is the Q over Q max. That's what we are plotting here as a function of X, the stem position or the valve opening. As we said, it goes from 0 to 1 or 0 to 100%, depending upon how you express it. If it is 0, then we see the Q min is 0.02 almost. It's not totally shut off, 0.02. So it's slightly right here. When X is 0.03, it's 30% open. You see, that's again very small. When it's 0.07, it's pretty widely open. So it's still 0.0637. But when you go near, so after that, there's a hyperbolic increase, and it's right here when there's the maximum controllable flow, you'll see this is equal to 1. Okay. So the flow is maximum. You reach the maximum control Q max right here. Okay, so what are the characteristics? By the way, this is a schematic one, not exactly according to database. In fact, it's something like this, something like this. Okay, um, control valve with the hyperbolic characteristics, very small flow at low openings, as you can see. At low openings, we have a very small flow. Flow increases non-linearly with valve opening. So it does not increase linearly. It increases non-linearly at small flow, and then suddenly there is a big increase. Okay. Sensitivity is low at low X. That means even if we change the valve stem position quite a lot, open the valve, the flow rate does not change that much. So very low sensitivity. But right here, near the maximum flow, we have a very high sensitivity. Slight change leads to a very big change in the flow rate. Okay. Um, these type of valves are used when a wide controllable flow range is needed. X is equal to 0, Q is equal to Q mean, that's a minimum controllable flow. This is not exactly a closed valve. X is equal to 1, this Q is equal to Q max, this is called maximum controllable flow. This is not, again, fully open, but very near to that. Okay. Next, of course, a problem. Once we understand these characteristics, the problem is very easy. R is equal to 50 is given, flow rate at 0 to 70% opening is given, and we want to know what's the flow rate at 30% opening. This is just a very easy one. Take the ratio. And so that's what it is. So all these details are given in this website here, and we get the answer as 2.225. So B is the correct option. Let's look at a practical example here. So here we have a caustic dosing to neutralizing tank. Normally, there is not much of the pH change, the acidic effluent feed, let's say from some kind of a nitration tank, so nitric acid. So normally there is not much change, but suddenly there is a process upset, or because of some reason, there's a big discharge. At that condition, we needed a very high flow rate of the caustic. So that's where this hyperbolic characteristic is important. So this is the caustic storage tank. Of course, we have a vent here. This is the neutralization tank. This is the starter. This is the motor here. And here we have a dual caustic dosing pump. This is what we have. This is a non-deterrent valve. This is flow rate indicating transmitter. This is, of course, an analyzing indeed transmitter. So it measures what the pH is, and correspondingly, this goes to a controller, analysis indicator controller, and that controls this control valve here. Okay. So, basically what we have in a chemical plant, acidic waste what we've neutralized using sodium hydroxide solution. So basically the flow rate is known from sodium hydroxide storage tank, from this caustic tank here, from this caustic tank. It goes through a pump, dosing pump, and then there's a hyperbolic control valve, and it goes to the neutralization tank. We know for flow to a valve, Q is proportional to this one. So we already know that since delta P and rho are constant, this is given in the problem. So Q is proportional to CV. So as you can see, Q over Q max is just, of course, is a ratio of CV over C max. So this is quite fine control at low flow. Not much of caustic is needed, but when there is a big upset in the process, and there's a large amount of waste acid comes in the effluent, then of course we need a big dosage of caustic. So that's where this hyperbolic characteristic comes in. So anyway, so the final correct option is, of course, this one. B is the correct option.